Hello again, folks. Today we're going to be working on section 12.5. It's actually just simply called the normal curve, but this is the actual subject. Gaussian, otherwise known as normal distribution. A big lump, if you will. It's for statistics, purpose of statistics. Today is, let's see, not quite December yet. Today is November 30th, and we are right on schedule for section 12.5. It was originally broken up over the course of 2 days, I believe, because there are 2 assignments in my lab. I'm just going to attempt to cover all of the material today, so that means I won't have a video for Wednesday. Right? You'll just have to work on part 2 of section 12.5. Okay? And then we're near the end. Let's see. The packet today is involved. All right. There are the diagrams that I swiped from the textbook, which I think are very nice. All right. There's a picture of rectangular distribution, of J-shaped distribution, and bimodal, and then examples of skewed distributions, skewed left or skewed right. This is the picture simplified if there were just a curve drawn over the peaks here, which is more often the case. All right, and then there's the actual normal distribution, which, if you notice even superficially right off the bat, is the most evenly distributed, all right, whether very tall or whether, shallow. All right, these are all examples of normal distribution. Okay. Now, if you don't watch this video, you still have the information in announcements. Or through announcements, I have a link to our pages. And there are some formulas and some rules. What I did was, also here's the formula for z-score. Very important. These are tables that you absolutely must employ. This very large, paper-long table, and then the other half of it. And you will be grateful that you have this, believe it or not. This will make doing the assignments easier. All right. And then there's finally, this is a procedure for finding percent. All right. Using diagrams or descriptions of diagrams first. I threw this in here. This is a diagram that I want to fill in with you. I made it my top page, but it's probably several pages down in the list. This is basically the normal distribution, how it's divided. You'll see that there is 1s, 2s, 3s on this side, negative s, negative 2s, and negative 3s on this side, and the mean in the middle. I just want to give you some information that you could fill in as we go through. It's actually listed here and here. And then there are the homework assignment, the sample, the examples that are in the textbook. We'll go through these. Okay. So, having said that, let me put this away. See if the light makes that any better or worse. Looks like it is better. Okay. It's raining torrentially out right now. Very ferocious. Well, better than it was. All right. Let me get your feet wet with some information that you already know. But would be good to keep in mind, right, where we are and how we got here. Right, let's think about this as sort of the evolution of a graph. Math world, as I'm fond of referring to it, is a coordinate plane for our purposes right now, and that is usually divided up into 4 quadrants, right? Let's just think of this as math world, the happiest place on earth. See? Happy. Alright, anyhow, these are all quadrants. None left out. Anything that is possible is in math world. Theoretically, or not. Well, math world is anything that is theoretically possible. Normally what you see on a standardized test is that they slim this down to just be the first quadrant. Right? They don't bother to label it as such, but that is really what it is. If this is 0 over at this point of intersection, and the axis vertically and horizontally is whatever they label it, unique to the problem, this is really just the first quadrant. Right, usually this is in, well, if this is math world, let's just call this business world, which is more concerned with practicality, or economics, or sciences. Or statistics. Now, what we could do, and this is often the case, in the statistics side of the tracks, if you will, arrange this just a little bit differently. It doesn't have to be, but it could be. Right? If you were to take a frequency distribution, which, as you know, is basically a T-shaped diagram that consists of classes and frequencies. So you'll see something like 0 to 3, 4 to 7, 8 to 11, and so forth. And then some numbers indicating how often they occur. If you take that idea and adapt it to a diagram like this, we get the histogram. Which is a glorified bar chart, except that there are no gaps between the classes. The one is butted up against the next. So you'll see something, frequency would be along the vertical axis, and classes would be along the horizontal axis. Then you would see, well, as I mentioned, if it's a glorified bar chart, and I haven't given this much detail, you would see bars that tall. So hypothetically, give it a little color, a bar like that, and in this class, a bar like that, and in this one, third bar, and you see it's staggered, this being a histogram. The next logical step is to basically narrow the width of these classes so that they're not so blocky. Basically, at some point, ask themselves, well, what if we draw a curve over it? You know, if I flesh this out a little bit better, I mean, I'm not being too creative here, but let's say that this is evenly distributed. And it looks like that. if you were to basically draw a curve over it, incorporating the peaks here, you'd see this lump, right? It'd be a little bit nicer drawing than I have it. This is an example of, well, a pretty good example of a normal distribution, because it is a nice even lump rather than a shifted, crocked sort of lump. Skewed would be the proper terminology. With a curve over the peaks. This is a normal distribution curve. And that is really the subject for today. I just, in a train of thought, taking it one step further and reducing the size of these so that there is no apparent block to it. It's just a smooth curve. Very narrow classes, if you will, infinitely narrow, so that it looks smooth. All right. If you happen, I mean, you're not required to have a graphing calculator, but you can get your calculator to draw a nice, smooth, normal distribution like this by typing in this function. Y equals, the most basic type would be, let's see, e to the negative x squared, something like that. That will produce this shape. Ski slope. Now let's look at the other types that are possible and give you some examples for each. I need a sip of water. As I mentioned in the handout, the actual drawings that I'm referring to would be on this piece of paper and the subsequent pieces of paper. But just to sort of summarize, as I'm inclined to do, here are some shapes of distributions. That isn't too faint. A very plain one would be, not too visually satisfying, would be a rectangular distribution. This is a situation wherein all the observed values have the same frequency. And a good example of that would be a die roll, at least in time, maybe not immediately, but if you kept rolling a die enough times, what you would see is that you'd have a graph that looks like this, right, where the 6 values, rolling a 1, rolling a 2, rolling a 3, rolling a 4, rolling a 5, rolling a 6, they all have the same frequency, right, over time. That would be a categorical frequency, of course, but that is the observed pattern. There's no lump per se. There's just this block, if you will, and the categories, which you could group them. They're kind of bunched. Normally what you would see on a categorical frequency distribution is an obvious gap, because they're not really classes in the classic sense. They're in discrete values, the sides of a die. Okay. Now the next one is the J-shape distribution. And this is in a sort of graph you would see when the frequency is either increasing or decreasing at a constant rate. Data taken of perhaps hours studied per week might behave like this. Either you start out, let's be very, very determined, and if it won't work for you, but perhaps if you you started out on Monday, coming off the weekend and a little tipsy, and you go, well, I'll just put in a little bit of time, and then you start to wise up, and over the course of the week, by Friday, you're like the most studious person in the world. All right, look at that. If this bar is any insinuation about how hardworking you are. Alternatively, perhaps you start out the week very inspired, and you go, hey, you know what, I'm going to put in 9 hours or whatever of studying, God bless you if you did. And then slowly your will is broken over the course of a week, and then by Friday you're like, yeah, you know what, the freak this, I'm done. It is a possibility. That would be an example of a J shape, If you can imagine basically a curve, that kind of looks like it's curving upward here or curving downward, sort of the mirror image of a J, depending upon which one you're looking at. That would be that. Then there's the Gaussian distribution, named after a famous mathematician. Carl Friedrich Gauss. My German is not so good, which is ironic because I am of that ancestry. It is called the normal distribution, and that is basically the pristine sort of shape that you had, well, I implied it before, which is basically this shape, the mountain, if you will. All right, and if you put a curve over it, a curve that looks like one of these three, perhaps. Lots of things simulate this condition, but we'll get into that. All right. The examples that are the textbook examples for today are all examples of normal distributions, so we'll come back to that. Then there is bimodal distribution. Let us see. This is an example in which two frequencies I feel like I'm spelling that wrong somehow, but no, frequent, U-E-N-C, yeah, I guess that's, don't know why that looks weird to me. Yeah. Two frequencies which don't have to be the same necessarily. Normally when we think of things that are bimodal, they are in fact equal in frequency. But when it comes to a graph, there's a little more leeway. They aren't necessarily equal, but distinct from everything else. Distinctly taller, you know. Which implies more frequent. Than all others. In terms of the ball height. If you, as an example, surveyed men and women for their weight, and you put that information on the same graph rather than distinguish it as a graph of men's weights per se and a graph of women's weights per se. Put them on the same graph. There's probably an average weight of men and an average weight of women. So you'll see not one big pile, maybe, but two distinct peaks. Example, I hate to say this, it looks like someone giving you the finger, but two fingers at the same time, you know, side by side. It's tasteless, right? I'm sorry, but that is a funny way to remember it. If you have a bimodal distribution, you're being flipped off twice, not just once, twice. You know? And then there are the skews. Skewed distributions are frequent. That is something of a pun. They occur, you know, the subject of skewed distributions comes up frequently. You could be skewed left or skewed right. So, to abbreviate, I'm just going to call this left here and this right here in the appropriate locations. And then give you some details. I think I'm going to have to dip this a little bit. There we go. There's an alternative way of referring to a left skewed distribution. What is implied here is that if there's a tail, sort of a narrow portion of this mountain range, the tail is favoring the left. And similarly, if you have a distributional lump that is favoring one side or another, the tail would be on the right. So it can be somewhat counterintuitive. Basically, if you have a left skew, that means that the mode, which is the frequency that occurs the most often, would be on the right, ironically. And in the case of a skewed right, that means that it's being pulled towards the right, but the mode is actually on the left. if you have an outlier in your data, oftentimes this is the way that a graph would look when they're, not exclusively perhaps, but this is usually when there are outliers present. One piece of data is pulling everything off to one direction. Bad seed, if you will. Here's a graph to indicate. Here you see you have skewed the right. So where is the mode? It would be this peak here, right? Would be the greatest frequency, right? And that is ironically favoring the left, you know. Whereas if you have a left skew, the mode is on the right side. It's favoring the right. Now, what is perhaps more important is where the other averages are in relation to each other. So let me incorporate that here if I can. And we'll separate it here. In the case of a left skew, right, the order, if you read from left to right, would be the mean occurs first, and then the median would be in the middle, and then the mode. So I'm using less than symbols just to indicate that one is less than the other. The greatest would be the mode. Let's see. In the case of a right skew, it is this exactly backwards. All right. You'd have the mode occurs first on the left, and then the median, and then the mean. I hope this is visible, and if not, I will rewrite it. That will be useful to later. Mean, median, and mode in that order for left. And then the reflection of that mode, median, mean for the right. Can't draw on top of the established color for some reason. And just erases. All right. This diagram again summarizes that. Notice the location of the mode here. For right skew, the mode is on the left. Anyhow, if you're reading from left to right, it would actually be that first. So technically it would be the smallest figure. Let's see. That's taking sign into consideration, not necessarily magnitude. Okay. All right. Now, take out this diagram. I have to draw it, unfortunately, but we'll discuss the Gaussian normal distribution now. So if you happen to have this printed, you have the information on it that really is all that is necessary to know about it, but I neglected to write something here. So I want to include that now. Let me see if I can get away with moving this without creating a disaster. And then putting this board in place of it. At least this has a graph to it. Hesitating. Let's see here. Jesus just died on me. Yeah, I corrupted it. That's better. Yeah, just died. Unless it was the grain. Nope, I gave up the ghost. Yeah. It doesn't like me, apparently. Here you go. Now a lot of times what happens, even though you may have a graph of a histogram that starts at 0 and it ends some other place, and the lump is like so. Oftentimes what a statistician will do is move the graph so that where the peak would be is exactly overlapping the location of 0. It doesn't have to be that way, but that is frequently the case. All right. Anyhow, which means that you go from basically a perspective of just being in quadrant 1 to technically being in quadrant 1 and 2 simultaneously. Again, they wouldn't bother labeling them as such, right? But those would be the places, if this is where the coordinate axis would be. Anyhow, on my diagram, it isn't for any special purpose. I have it incremented on graph paper here. I just tried to make these columns here, if you will, evenly spaced. So I just decided to do 5 this way and 5 this way. It didn't have to be specifically 5, just has to be consistent. So I'll be like that again. Okay. So I'm just going to put dashed lines now, and you'll see why momentarily. Now, as I said, if you took a distribution and you just shifted it over so that what would be the average, that is the mean, would overlap where 0 is. All right. Now it will be in respect of something called standard deviation. You remember the last section, which was 12.4, right? We calculated standard deviation as a number meant to give you a feel for how things vary, right? Or, what the average distance from the mean would be. The average distance. All right. Now, you could, if you went one unit, if you will, out towards the right, away from the middle, the mean, that would be one standard deviation. So we'll just call it 1s. If you went towards the left, one standard deviation would be negative 1s. Right? And 2 standard deviations would be negative 2s, and 3 standard deviations in this direction would be negative 3s. And in theory, you could keep doing this, but eventually it'll get narrower and infinitesimally small. On this side, just to complete this thought, positive 2s and positive 3s. Now, I just drew a generic sort of lump here, but I'm going to try to be consistent so that it looks nice. Let's see, 1, 2. Doesn't have to be incremented this way. But it should be symmetrical. I live in South Amboy, so the church bells are ringing. Anyhow, here's a badly drawn normal curve, if you will. Now, what is true characteristically of a normal curve? I already kind of alluded to it, but the criteria would be, number 1, it is bell-shaped, and bells are not slanted usually, not messed up, unless they are messed up. It would be, more importantly, symmetrical about the mean, x bar. And if you analyze the averages themselves, interestingly, different from skewed, the mean is going to be equal to the mode and the median. That is perhaps its most famous and useful characteristic to know. The mean, median, and mode are all the same value. One is not greater or less than the other, or the either two. Okay. Another interesting fun fact, and this is really what I wanted to fit into the rest of the drawing here that I haven't included. In terms of percentages of data, the percent of data out of the total that fits underneath this curve, and you could scribble in between these columns exactly like so. This is a percent of data. That would fit within one standard deviation either way. that is from here to here, is 68%. The majority of the data would be within one standard deviation either way. That is total, which means technically 34% in this column up to the roof here, and 34% this way. Unless you have greater precision than just a whole number, whole percent. The percent of the data that would fit underneath the roof here within 2 standard deviations, that is from here to here, would be 95% of the data. That is the 2 here and the 2 here combined. Right, which means that, and maybe it would be easier if I just wrote it up here. If you wanted to think of these as being sums, if this is 34%, then this would have to be 34 to account for the 68 total. Right? Depending upon the degree of precision, the next column here to make it 95 from here to here would be 13.5 and 13.5%. I don't know if that's faint, so let me write this a little darker. There you go. That's better. Each column would be technically this much of the data. And then lastly, at least for use, common use would be the stretch of the data from here to here. Right? That comprises nearly all of it. The amount of data that is present onto this roof line here would be 99.7% total. All right? And as you can see, in theory, you could stretch it out to a 4th standard deviation in this direction, and a 4th over in this direction. And the thing is, it will approach 0, the line here. This curve will approach the x-axis, but into infinity, it will never reach it. All right, so you'll get tinier and tinier and tinier percentages, mathematically speaking. Right? So usually when we hit 99, a person is pretty content with that and go, all right, I'm not going to worry about a fraction of a percent, because even a percent is a fraction of a whole number. So anyhow, if you were to divvy this up, these 3 columns this way and these 3 columns this way, it might be something like 2.35% here and 2.35% here, to account for 99.7 from 3 to 3. Right? That is the information that I left out somewhat purposely when I printed this, because in a class, if we were together, I would have you fill this in as a device for helping you remember it. Right? When you write something, you're more inclined to remember it. Anyhow, you could verify. If you add 34 and 34, you indeed get 68. Right? If you add 34 plus 13.5 and then multiply by 2, what do you get? You should get 95. All right. 13.5 rather plus 34, 47.5, right? Times 2 is your 95. All right. And then an additional 13.5 plus 2.35, 34. This half would be technically 49.85 times 2, 99.7, right? Okay. Let me get a sip of water, and I'll be right back. Anyhow, this collectively, which I put up in this word balloon, the green percentages and the plus or minus 3, 2, or 1 standard deviations, is referred to as the empirical rule. Okay. And these are the conditions over in this thought balloon of what qualifies as a normal distribution, right? So red is what is the how we decide something is normal or not, and green is what we call the empirical rule, to summarize. Right. Now, this is the purely numerical math purist way of looking at it. Just numbers involved, nothing really special. If you take it from the perspective, to the extent, look at it to the extent of a statistician, I should say. Right? This column of data, which I'm going to highlight here, is under a curve. Right? In the field of calculus, right, one of the famous problems of calculus is to calculate an area under a curve. In calculus, you use formulas and techniques to basically find area that it is irregular somehow. So area under a curve. This is not perfectly rectangular, you notice, right? It has a sort of a furniture-esque sort of scroll to it here. It's fancy. Anyhow, the techniques of calculus are about that, finding area of irregular shapes, or area under a curve is another example of that. To a statistician, though, this is not practical unless you could apply it to something like, say, probability. Well, what is a good thing to keep in mind then is that the area of the normal curve, a chunk of it or the whole thing, corresponds to a percentage, right? We already established that. But the percentage itself is a probability, or it can be thought of as a probability. That is its practical usage, right, in statistics, right? Making predictions. Okay, so for right now, think about it that way. This isn't just an area, it's a percent, and a percent could be interpreted as a probability. Okay, let me get this out of the way. This is our overview. Let me erase this now. Get that trigger. There we go. Before we get into the next thing, the z-scores, let me remind you of something from, it is technically MAT-114, so the first semester of this class. but it's basic arithmetic. Right. We have in the subject of arithmetic and also MAT-114 this concept. To make it worse, well, because that was dopey. I need to clean that again. We had discussed a while ago, not this semester, but last semester, if you took that class, percent equations. Which is a little misleading because there are technically three, and one of them actually looks for a percent. They all involve a percentage somehow. So the labeling that I was taught is part, base, and percent itself. In other words, you'd be looking for this number that is doing this job, if you will, looking for this number or looking for this number when you're given a percent equation or employing one. Right? If you had a question like 50% of 20 is what? This would be an example of a part equation. The part is this what. It's the thing that is a portion of the original amount. And it would be sitting in this position grammatically. One thing I like to teach about this is that it is a good basis, springboard for learning to decipher word problems. In other words, translate something that is verbal into something that is more symbolic, more mathematical. The word is the equals, right? The word of is, in this context, times. So if you had 50% of 20 is what, then that really means that you're either going to use the decimal equivalent, 0.50, times 20, and you'll get a number. Or you could alternatively use 50 over 100, which is just 1/2, the fractional form of this, and get the same answer. What's half of 20? 10, right? Anyhow, if the question of what you're looking for is in this position, either is at the very end of the question usually, or at the very beginning, in other words, find such and such, or what is, instead of is what, that is the part. It is a portion of the original amount. As you can see, it is purely arithmetic. It is just multiplying two things. If on the other hand, I just phrased this a little bit differently, and you had something like, I'm not too original, but 50% of what is 10, and now you see that the position of the actual question is now in the middle of the sentence, right? This is the base, right? It is the original amount, right? You might think of it as being the whole, right? In this case, you're still going to translate those words is and what, is and of, to their mathematical symbol, but you're going to employ algebra in a case like this. So you might have something like 0.50 times, let's just call it B for base, equals 10. In order, this sets you up for a one-step algebraic equation, in which case you would perform the opposite operation to solve for the variable. Right? In other words, to get this b alone, you would have to move 0.5. How do you do that? Via opposite operations. If it starts out as a multiplication problem because of the word of, in order to justify moving it over equals, you would divide by 50%. And this realistically is going to be the same relationship as 50 into 1,000. How many 50s can you squeeze into 10? You can't. How many could you fit into 100? 2 exactly. And the decimal is there, so it's 20. So your base would be 20 in this case, which is good because I wasn't being creative. Then lastly, if you had the question phrased like so, what percent of 20 is 10, you could usually identify this as being the literal percent equation out of the 3 because it is the question of percent itself. You could rewrite this as, well, let's just call this P, and this of is still times, and this 20 is still sitting here, and equals is still there, and that's 10. This is, again, another one-step algebraic equation. There is an added step in here, though. In order to solve for P in this case, you would indeed have to move 20 over the equals, and you would do so via opposite operations, which means you would divide by 20 here and here. And the 20s would cancel, just like these 0.5s cancel. And you just have P equals this fraction. But here's the thing. Whether you simplify it or not, now that's 10 over 20, which, you could pull some mental math tricks. Cross out pairs of zeros, it's 1/2. And you might just recognize, well, 1/2 is 50%, right? You need it to be given in the style of a percentage rather than in the style of a fraction. So in order to convert a fraction to a percentage, there is in some cases a way to do that directly, but usually what you end up having to do is to convert it to a decimal first and then convert that to a percentage. Bottom line is that you're going to be multiplying this by 100% one way or another. If you divided the top by the bottom, that is 1 divided by 2, that will give you the decimal. 1 goes into 2 exactly twice. Backwards, I'm sorry. 1 here, 2 there, a couple of zeros. 2 doesn't fit into 1, it's too small, but 2 goes into 10 exactly 5 times. That will give you the decimal 0.5, just doing this division. If you multiply by 100, the effect is that the decimal point moves. So you would end up with 50%. This is an added step, right? The percentage is in fact 50%, but just remember to do that if you had to. Now, the stuff that we're talking about now is going to involve percentages, possibly. So you would need to remember this older material. Get rid of that. And we'll move on to z-scores. Ooh. I hope I didn't break it. That would be terrible. Where is my calculator? There it is. I never leave things on the windowsill. And he promptly puts it back because I need to. I don't have any space. Alright, moving on. Alright. The next thing is a discussion of z-score. Alright, here is the formula for z-score, but let me establish why we're even going to look for this. Okay. As I was mentioning before, an area which is under the curve, whatever chunk of it, corresponds visible, looks like it is, to a percentage. And the percentage can be used as a probability. Used to predict. But how do we get the area? Well, the area itself comes from something called a z-score. And the z-score itself corresponds to an area. Ultimately, what is a z-score really? A z-score is a ratio. A ratio is a decimal. And because we have a table, we could find out what the z-score corresponds to as an area. Right? So we have this ratio, which is really dividing two numbers, establishing what that decimal is. Right? That is the z-score. Looking it up from a table, what the area would be, and then potentially using that to figure out what it is as a percent. And then a little bit further down the pike, the train of thought would be, well, what's the probability? Okay? In calculus, the subject of calculus techniques would be used to find an area. Right? But we don't need to do that. We have a table instead, right? Which is true because we have a ratio, right? And ratios are true for anything that is proportionate. Right, that is what this is, right? And you will employ this a lot. All right, so you definitely want to print this, right? This is a z-score table, right? And what you see is the z-score written as a decimal. All right, and then you will see what that correlates to. These are areas. Right? If you had a z-score that went to the 100th place, then you would read that here, right? Whatever it is, if it's a 1, a 2, a 3, a 4, all the way up to 9. Okay. If you just have it as far as the 10th place, then this is sufficient, right? It really is 0, 0 here. Right, is the hundreds. If you just have something as far as the 10th place, then the hundreds column would be 0. Right, and you would read these values that my finger is pointing at. Right, there are 2 pages of this. Right, because your z-score, depending upon where you're taking information from in the calculation, could end up being a negative, right, or it could end up being a positive. Right, we'll do a couple of these. Right, but you definitely want that table. Right. This is the z-score formula. It is equal to whatever data value you take subtracted from the mean and divided by the standard deviation. All right. Remember, not to obsess, but what is standard deviation? This is fading. The standard deviation is kind of an average, right? An average onto itself distances to the middle. Right? The middle is usually the mean. Right? The average overall. An overall average of distances to the mean. Right? This is going to give you the exact distance to the mean. The exact distance to the mean. All right. So if you take the individual data value and then compare it to the standard deviation, which is itself the overall average, you might see exactly 1 as an average, all right, for your z-score, or you get some decimal, right? Something greater than 1 or less than 1 or negative or positive, right? Depending upon whether you're on the left side of this or on the right side of this. Okay? Anyhow, dividing this exact distance by the average distance is going to produce a ratio. Right? And that ratio is the z-score, which corresponds to an area. Okay? So, if this is better or worse, let's do some problems. Yeah, to give you a feel for this, if you look in the back of this packet, there's the list of example problems. So we'll do a couple of these from number 1, which is just employing the empirical rule, all right, the percentages. Okay, to read this, the heights of females, the heights for females that are the same age are normally distributed. Right? When they tell you that something is normally distributed, get in the habit of drawing a lump like that. Something is normally distributed, it's going to look like that, the data. In a random sample of 500 females, determine the approximate number of females in the sample who are expected to have a height within 1 standard deviation of the mean. To answer part A to this question here, and then eventually part B, within 1 standard deviation means 68% is the number that you're going to use. All right. The second question is figure out how many out of 500 are within 2 standard deviations. You can get an actual number of people within 2 standard deviations. Means you're going to use 95%. This is going to translate to basically this. I mean, I didn't say it explicitly, but you take that 68% and you say, well, 68% of 500 women is what? To dumb it down to just a 1-sentence word problem. And you say, all right, well, love is times, and is equals, and 500 is here. And 68% I'm either going to make as a decimal, which is probably the more practical, or you could make it as a fraction. Right? 68% is literally 68 over 100. In that respect, it would be easier to use, because then you could pull some mental math tricks. Either do it this way, or do it this way. If you're using a calculator, perhaps this is faster. Right? If you're just using it, your own wits here, 100 as a denominator crosses out 2 zeros here. And then it is the equivalent of 68 times 5. Which would be 340 women out of 500. The height of females with the same age. All right. Right. 340 women out of 500 surveyed fit within 1 standard deviation. That is not implying if this is the mean here. That's 1s and that's 1s negative and 1s positive. It doesn't mean that they themselves have the same height, but just it is suggesting that these 340 women are this far away from the average within this section of the lump, that of normal distribution lump. They're not outside of that, they're inside of this. If you calculate the number of women within 95%, that would be a larger chunk of 500. That is like phrasing the question this way. You'd be asking yourself, 95% of what of 500 is what? And then just reinterpreting it like so. Of is times, is equals, 500 is here. This is the question of n, 0.95 times 500. Or you could pull a similar trick here. 95 over 100 times 500. If you're dividing by a common factor here, you can simplify. 2 zeros here, 2 zeros there. And then it is realistically the same outcome as 95 times 5. 475 women. Notice that it is more ladies because I'm using a larger percentage of the data. How many of these 500 women fit within 2 standard deviations? They go a bit further. They would be out to here, negative 2s, positive 2s. Let me get a drink. All right, number 2. We'll calculate z-scores from scratch now. All right. Number 2 says a normal distribution has a mean of 60 and a standard deviation of 15. All right, determine the z-score for the following data values: 75, 81, 60, 33. All right, this is pretty straightforward. In example 2, if you're given the mean is equal to 60, and looks like an omega, and the standard deviation is equal to 15. And for A, B, C, and D, we can calculate the z-score. Z is equal to the data value minus the mean over the standard deviation. It really is just a matter of substituting and then dividing. Well, subtract first. And then divide. Okay, so in the case of A, they want you to find where, let's see, we're going to calculate the z-score for 75, 81, 60, and 33. If the data value is 75 and the mean is 60, as it will be in each of these cases, that isn't going to change, nor is the standard deviation of 15 going to change. Then in the first instance, it's going to be 75 minus 60, which means that your z difference up here will be 15. And if you divide by 15, then z is equal to 1. What does this mean? It means that the data value otherwise known as 75 is one standard deviation above the mean. That is what this 1 means. If you did this calculation, substituting data value 81, maybe use a different color. The difference of 81 and 60 is what? 21, right? So z is equal to 21 over 15, right? And in this case, no matter which way you slice it, you're going to get 1.4. Okay. Which again, what does z equals 1.4 mean? It means that the data value 81 is 1.4 standard deviations above the mean. Remember, this is a ratio of an actual example of a deviation, a difference from the middle, and the average of those. So if you have a ratio of 1, that means that it is exactly 1 away. If you have a ratio of 1.4, that means that it's 1 away from the middle. Now if you substitute 60 in here, watch what happens. 60 minus 60 is just what? It's 0, right? What is 0 divided by 15? It's just 0. If to this point we have decided that the z-score means that the data value is so far from the mean, and you have just this value of 0, that's kind of implying something. It means, I hate to use the word means, right? It means that the data value is 0 standard deviations above or below the mean. If that is the case, that you are neither left nor right, that is backwards, sorry, left or right, the other right, what is that implying? This is implying that 60 is, in fact, the mean itself. Because remember, the lump that is the normal distribution has been scooted over, right, from just being in quadrant 1, wherever the mean happens to be, to coincide and to overlap with 0 exactly. So if you just moved all of your data this way so that it is now the middle is overlapping, is superimposed upon 0, then that is what the mean must be, right? The mean must be 0. It's at that location, right? The value is actually y, right? It's a frequency, right? Okay, last one. If you substitute 33 in here, 33 minus 60 would be 27, right? Negative though. Negative 27 over 15. Right, and if you simplify that, whether way you do it, you're going to end up with negative 1.8. The negative implies direction, right? In this case, it means the data value is 1.8 standard deviations below or left of. To the left, as opposed to the right. Okay. Let's see, an hour and a half. Let's take a look at number 3 here. determining the area, right, onto the normal curve, right? There's a process to this. It is summarized really by this. There's an added step here I want to say, but this is basically the process, right? If you were looking for a percentage, right? We're going to go somewhat halfway there. Right now we're just looking for areas, right? Learning how to read a table, right? So when we get to example 4, then we'll go the whole 9 yards. But for right now, we're going to determine the area under the curve, right? To the left of z-score -1, right? What you want to do is basically draw a picture. Get in the habit, as I mentioned earlier, of drawing a picture. So it doesn't have to be beautiful, it just has to be a lump like this. Right. So I would put in some essential features, a little bit more detail than just simply the lump itself. All right, but based upon the description. So if you have given this information, put that back. If you draw a normal curve like this, the 2 features you should include every single time is a little dashed line indicating where the middle is. All right? This is the average, right? Right here. And it is also 0, right? Where would -1 be, since we're answering question A, right? All right, data. The area left of z-score -1.00. That is basically the question. In respect of 0, a -1 would be on the left side of it, right? So just draw another simple line like this here and label it -1.00, right? Now, if we're talking about an area, that is the barrier, basically, of the area. This is the point of the picture, to give you an idea of how much you should get and its location. Shade in up to that point. All right? We're looking for this area. It's not going to be the most satisfying area that we're used to, like, like so many inches square. But we'll have a decimal that we can get from our table. All right. If you now look at the table, and you would have to do this every time, go to the location of -1 on the table. It starts at -3.4. And here's -1. Now, the reason that we would read just this first column and not something beyond it is because the decimal is actually -1.00, which is what this column is accounting for. That the hundredths place is, just 0. If the hundredths place is 1, then you would read this column. If the hundredths place is 2, then you would read this column. If the hundredths place is 3, then you would read this column, and so forth. All right, anyhow, that is the area, as unsatisfying as it might be. Because we're used to seeing a unit when we see an area, but it is a ratio. So 0.1587. Remember, if z equals -1.00, right, and that corresponds to an area that is 0.1587. Which itself corresponds to a percentage of the data, which again you could be used for probability. try not to erase too much between these. All right. If we do B, we'll find the area left of z-score 1.19. All right, again, draw a simple picture to illustrate the description here. So you have a normal distribution lump, right? The average is always in the middle of the lump here, and that also equals 0. So where would positive 1.19 be in respect of 0? All right, it would be on the right side of it. So just draw roughly an increment this way, all right, and label it 1.19, and then scribble in what is left of it. So we're going to get this area of the curve that is beyond it, left of that. All right, and again, we'll go to our table and read that. All right, you're going to have to use the other table where the positive z-scores are. All right, and here you have it. Go to 1.9, which is right here, and then realize now we have, pardon me, 1.1. 1.1 is here, and then because we have a hundredths place of 9, we would have to go all the way to the end of this and go right there, right? 1.19 corresponds to the area of 0.8830. So if our z-score is 1.19, then the area is equal to 0.8830. Moving on. Now it gets a little trickier, all right? Because then you're asked to read from the right. All right. Find the area, which is why the picture helps to establish what you're doing. Area right of z, same place, 1.19. In this case, the phrasing would imply that instead of the lump, that portion of the lump that is to the left of 0, pardon me, the left of 1.19, we'll be starting or looking at this same place, 1.19, but we're actually covering a lot more area. We read left to right, right? So we're going to find all of this area. We can expect a different value. I'm sorry, I have these backwards. I'm looking at my camera a lot, and my camera unfortunately is the mirror image. So let me switch this. This is the solution to C, all right, left, no. Learn your left and your right. This drawing is for this picture, this situation here. This drawing is for this situation here. I'm a little spun out of it right now. The area left of this is this picture. Okay, so I have to fix this, I'm sorry. That is the left. And that is why the value is very close to 1. 1 is the maximum in terms of an area. All notice that this is 0.8. It's nearly on top of it. All right. This is the area to the right, is as I had illustrated it initially. I'm sorry. See, if we were in person, I'd have a bunch of people telling me, "Hey, Dopey, what are you doing?" And I'd be grateful, because then it would be on track here. Sorry about the hiccup there. Okay. Of course it does. Perfect timing. This is left. This is right. Okay. All right. Now, here's the thing. Because all of the area calculations, this is part B, and this is part C, because the area in the table is read and calculated for left to right, all right, we have an issue when we get to something that is reading it from here. All right. The last problem intuitively gives us the value that it should be. All right. 1.19 is all of the area from the left to the right, up to that point. But what if we want to be beyond it? Right. There's a couple of things we could do. The easier thing to do is to use symmetry. Employ symmetry. If we could figure out, hypothetically, and I'm going to have to erase something here. If we could conceive of this situation, the area, if we had for negative 1.19, then we could just say via this case of symmetry that this would have to be the same magnitude as this area here. Right, so the shortcut is to basically go to, ironically perhaps, negative 1.19 in the table, and that will just give you the same value that would be here. So in this case, let's see, wrong table. Here is negative 1.1. I'm going to go all the way to the end. What am I saying? Stop reading things backwards. Yes, here we go. Negative 1.1, and then go all the way to 9. This is the area, 0.1170. .1170 is this area. All right. to this problem, C, to calculate that. If you do it in a slightly more complex way, and I'll do it now just for the sake of argument, you would have to do a little subtraction. Basically, this is the alternative. The area to the right of positive 1.19 would be the area that is the total area minus the area from the left. Positive 1.19. Right, you're going to get this value, right? Either way, either employing a shortcut or looking at it from the perspective of I'm going to subtract out all of this. Right. If that was, we had decided before, 0.8830 for this. We could just infer, they don't need a table for this. What is the total area going to be? The maximum is 1. So if you subtract 1.0000 by 0.8830, what would you get? That difference. Right? Right. If basically from here to here is 1, and you take out the green chunk that is 0.8830, that leaves you what is technically in blue in this drawing, which is this, 0.1170. Right. Do it that way, or just employ symmetry. All right. Look at what negative 1.19 would be, and then just substitute it for this value here. That's faster, but this is also good to recognize that that is the actual relationship. All right. The area table, as I had, is read and calculated for left to right. Meaning that you start here on the left and then you come to a screeching halt here. Right. All right, one more of these. Let's see. All right, the last one of this set. This is example 3D. All right, if we calculate between 2 points, area between 2 points. Z equals negative 1.62 and Z equals 2.57. Okay. Again, draw a simple picture. Is our distribution lump. Here is the middle. which corresponds to 0. Where would a negative be in respect of 0? A negative would be over here. So negative 1.62, doesn't have to be perfect, of course. Where would a positive be? A positive would be on the right side of 0, so maybe there. 2.57, right? And we're trying to get the area between them. So I'm going to shade this much of the lump. Make this a little bit more distinct from here to here. All right. In an instance like this, here's sort of a general formula. The area between will be equal to a larger area minus a smaller area. It isn't going to be 1 per se, but it will be some portion very close to that, perhaps. So here's what I mean in terms of larger and smaller. If you can imagine, let's say you're starting here, and this is where you end. The area from here to here would be a larger area from this starting point to this end point. On the other hand, if I started in the exact same place, but I ended here instead, that is the area from here to here, this would be a smaller area. I can more or less get the total from here to here and then subtract out that chunk. So you have to read the table twice. All right, read the z-score area for 2.57, then read it for negative 1.62, and then subtract out that smaller chunk. So in this case, 2.57, we would look at this table. Here's 2.5. That's 0, 1, 2, 3, 4, 5, 6, 7. This is the 7 column. You would have 0.9949. Substitute it for this. And then for the smaller one, you got to go to the other table because it's the negative table. Go to 1.6 first. Here is 1.6, negative 1.6 is here. This is 0, that's 0.61, 0.62. This is the 2 columns. So 0.0526. Right, and then subtract these values, and that will give you just this in between here. Okay, what do you end up with? You should end up with this 0.9423. This is the area between. save this because you will use this a lot. Here's the last thing and then I'll stop. This is a summary of much of the same information but with an added step, right? If you're going to calculate a percentage, all right, remember what I said. We're going to have a z-score, and the z-score is going to be interpreted as an area, and then the area will be interpreted as a percent. That is the train of thought. I gotta get a drink. If you look at example 4, it is about IQ scores. What you see here, intelligence quotients, IQ scores are normally distributed, which means that they behave in a manner that the data will look like this lump. X. With the mean of 100. So the mean of 100 would be here instead of using 0. This is an example of, this is not shifted over per se to be 0, but we're going to think about it that way anyhow, right, to use our tables. Right. This is why we'll be using percentages. If you're given that the mean is equal to 100, and then further on it goes to say that the standard deviation is 15, all right, determine the percent of individuals with IQ scores below 115, then below 70, then in between 2 points again, right, then below 130, then between 2 points again, and then above a certain point. All right, again, in each of these cases, I would draw a picture. Where on this table, all right, for the example A, we're looking for a percent based upon this value, condition below 115. $115 would be to the right of 100, so you would put a little mark like this and label it 115, and then for the sake of clarity, hopefully, shade in that much of the lump up to that point. I think my red is dying now too. It's a bit of overkill, but you get the idea. All right, as you can see, quite a chunk of the population would be, if this picture is any indication, under that much of the distribution. So, what do we need to do? We need to calculate a z-score first, and then interpret that as an area, and then multiply by 100. Z-score area, which is going to be in the style of a decimal, times 100 will give us a percentage. So, we'll calculate a z-score. Z is equal to the data value subtracted from the mean in this case over the standard deviation. To this point, the z-scores were given to us, but now we're going to calculate them. So if you put in the given value is 115 and the mean is 100, we'll have a positive, and the standard is 15. 115 minus 100 is z is equal to 15 over 15 again, all right, which means 1. So 1.00 is where we're going to look. All right, again, not to beat a dead horse, but we will go to the table. Look at the positive z-scores, go to 1, and then the first column is 0.00, so 0.8413 is the corresponding area. Area is 0.8813. That is a decimal naturally. We're going to multiply by 100. All right. The effect of multiplying this by 100 is to just scoot the decimal place over twice. So the percent below 115 is 88.13% of people, at least involved in this survey, right? Okay. This is the next one. For B, the description is the percent below 70, 130. Again, if you draw a simple picture, and this is the average of 100, and 130 is still a positive number, so it is on the right side of 100, just a little bit further along. So in theory, you have more of a shaded lump, right? A little bit further along toward the right. So again, calculate a z-score rather than have it given to you. Interpret that as an area using the table rather than calculus, then multiply by 100. All right. Z is therefore equal to the value minus the mean over the standard deviation. So if you insert 130 here, you're going to subtract from 100 and then divide by 15. 130 minus 100 is naturally 30. Divided by 15 is 2. So your z-score is equal to 2.00. Right? This correlates to an area of what? Look at the table. Still positive, so we're going to look at 2. 2.00 is 0.9772, it looks like. Yes. Okay. 9772. It's got more for there than needed. When you're converting an area, which is a decimal in this case, to a percentage, you're just multiplying by 100. So that is scooting this decimal place over twice is the effect. The percent below 130 is 97.72%, which is quite a lot. All right. C, 4C, not to be confused with the seasoning, is below 70. So in terms of the picture, here's our distribution lump. There's the mean, 100. 70 would be where in relation to 100? It would be to the left. It's not a negative value because it's not superimposed over 0, but you could still situate it. All right, so let's just say 70 is about there. This chunk of the population, this sample here, would be representing that much area. So you have a z-score of 70 minus 100 over 15, and you'll get a negative in this case, which means you'll have negative 30 over 15, which is a z-score of negative 2.00. Right? The area that corresponds to negative 2.0 is the other table. Negative 2.0 is here, and that's the first column, 0.0228. And then you're just going to multiply by 100 again, and that moves the decimal point over twice. So 2.28% are below 70. D is between, let's see, 70 and 115. We'll have to employ a little subtraction in this case. 100. It seems redundant maybe to draw the same picture over and over again, but I would do it. I'm trying to set a good example because it will help you decide what chunk of the area you're really looking for. 70 in relation to 100 would be here. 115 in relation to 100 would be approximately here, and that means that this is the area. It's like a ghost. Not beyond it, not before it. All right. Now, as before, the general idea is to do this. When we get to the area between will be equal to the area of the larger area minus the area that is the smaller area. We're going to have to find z-scores for each of these, nonetheless, because that's still the train of thought. Looking for a z-score, it's not given to us. We're going to find an area multiplied by 100 still. Basically, this is always going to be the start. Right, but these are going to be two different ends. You're going to end here, and you're going to end here. Right. This first is the small area, and consequently the smaller z-score. And this is the large z-score in area. So, the first one z small is 70 minus 100 divided by 15 again, which we already calculated actually. And what do we get? We got this, right? This is negative 30 over 15, which again is 2, negative 2. So that means an area of the small area is 0.0228. Save that number. The z-score of the larger area is 115, which did we also do that as well? We did. Okay. 0.8413 is ultimately what it is. Because if it's 115 minus 100 over 15, you're going to get 15 over 15, which is 1.00 positive, which is area of the large, 0.8413. Okay, and now you're going to substitute. So, in place of this larger area, 0.8413, in place of the smaller area, 0.0228, subtract them. The area of just the in-between here would be 0.8185. Right, which again, if you now complete this train of thought, multiplied by 100, you are going to just scoop this decimal place over twice to the right, which means that the percent is 81.85% between. And whether it's narrower again, if you have another between, it'll be like that. Right. Here's E, we have a smaller between. The percent between 115 and 130. Is our lump, is our middle, and here is 115 and 130 in respect of each other. Right. Remember, when you're reading the diagram, the table though, this is where we start reading from. This is where we end first, and here's where we end second. Right. From here to here is the smaller area, believe it or not, and from here to here is the larger area. So we're going to still employ this idea that the area between is equal to the area that is larger minus the area that is smaller. Right, but we need to calculate a z-score first for that, and a z-score first for that. And then subtract these. The z-score for 115 we already had is now the low end here. This is 0.84, pardon me. The z-score is, let's see, 1.0 in this case. And positive 2 in this case. Right, and that corresponds to an area of 0.8413. And this corresponds to an area of 0.9772, which if you subtract them, you get an area of 0.1359 times 100. This is the effect of just moving this decimal twice to the right. So this is going to be 13.59% between 115 and 130. The last of this set is above a certain point. So, pardon me, F is the percent above 122.5. Again, draw a picture, distribution lump, this is the middle at 100. 122.5 in relation to 100 is again on the right side. So you'd have a line about there, 122.5, and it is above in this case. So you would have to scribble in here into infinity in theory. All right. Now, this is an example again of where you could use symmetry, would be a shortcut. We still need to calculate the z-score. There's two ways to do this, remember. If you want the area total, the area to the right, this would be equal to the area total minus the area to the left. Right? Or, right, employ symmetry. I'll do it both ways. Erase this for the sake of space. Let's do it the more brute force way first, and then you might appreciate this more. I use Roman numerals just to distinguish it. The total area is always going to be 1.0000, as many zeros as you need. The area from the left, that is starting here and ending here, would be subtracted out of one whole, which would in theory be all the way that way. All right, and that will give you the chunk that is left over. We still need to calculate a z-score here first. All right, so the z-score would be 122.5. I hope that isn't too faint. That's better. 122.5 minus 100 divided by 15. And that would give you naturally 22.5 divided by 15. And what you would end up from this is the z would be 1.50. Right. And this will correspond to the area at 1.5 positive. So 1.5 is here. 0.9332 it looks like. Am I reading that backwards? No, it's right. Yeah. 0.9332. All right. Now that we have an area, and we could always assume that the total would be exactly 1, we could subtract from 1 0.9332. And use my calculator and drop something in the process, because that's what I do. 1 minus 0.9332 is 0.0668. 0.0668, who do we appreciate? Okay. Then, again, complete this thought, multiply by 100, you have a percentage. Scoot this over, you have 6.68% above. And so not a lot. Now, again, the alternative, and this is probably more efficient, right, is to employ symmetry. If you simply go to where you calculate a z-score, right, you would still have to do this, right, using the figures that you have. Unless you finagle what the equivalent would be here, negative 122.5. You're going to end up with a z-score that is negative 1.50. Right? And then you would use the alternative table that gives you the negatives, and it should just give you this area directly. So let's see. Negative 1.5, here we go. Yep, 0.0668. 0.0668. That would be the area here, all right, which would, by virtue of symmetry, would have the exact same area here. It's just on the opposite side, all right. Times 100 is 6.68%. Do it either way, just realize that you have options, right? Better to have choices, right? To have a choice is always ideal. That's very American, right? Freedom of choice. Okay, right. As I mentioned, this diagram is really a summary of that. Right, and these are different cases, right? What you would do. All right. The problem that is 5 is virtually the same exact process. So rather than beat a dead horse, and pun intended, because it's about horseback riding, I will spare you that. I'll give you the answers. I'll just write them here, and then I'll let you go. All right. Let's see. Come on. All right. For example 5, it's the same thing, really. You have A, B, C, D, and E. Percent of horseback rides last at least 3.2. This would be 50%. All right, this is 15.87%, 10.56%, 81.85%. And then this one would involve actually multiplying by the percentage. So you'd have 53 rides. Okay. Okay. All right. Let me just mention, for part E here, you had calculated, you're going to employ something that you calculated earlier. Right? What percent of horseback rides last at least 3.7 hours? That would be that percentage. All right. Now, if you took this 10.56% of 500 people, you could figure out is what figure. You're getting, it's a part equation, basically. So you have a percentage that you need to convert purely to a decimal. So bear in mind, I know there's a decimal point written into this, but it is a percent. All right, so you're either going to make this into a fraction, which would be a little more arduous in this case, or make this into a decimal purely. And I would go that route. What does it mean? Well, if you have a percent, it means divide by 100, so the effect is that you're going to move your decimal place twice towards the left, which means that you would have 0.1056 times 500 is the number of people. So if you type in, work with me here, 0.1056, the decimal equivalent of 10%, 10.56%, times 500. Then you have it 52.8, which is approximately 53. About equal to 53 rides. This is 52.8. Okay, that is how you would account for this. This is the only thing that would be, extra from this slew of problems. All right. As I mentioned, that is all of section 12.5. So, although it is, again, the schedule is broken up over 2 days, that is merely for the fact that there are 2 assignments for 12.5 in my lab. So I won't shoot a video because we covered all of the material, but do work on 12.5 homework 1, all right? And then perhaps on Wednesday as well, do 12.5 homework number 2, right? Then the very last thing will be on Monday, 12.6, and then I'll make a test number 3 and I'll tell you about it. Okay, so just work on this because we're very near the end. All right. Thank you, folks, for sticking with me. Sorry for the hiccup in between. Like I said, I'm reading things backwards. Have mercy. Be careful out there.